everybody, Solomon Saduma here again. Before I begin with lesson number 7, I want to thank everyone who's been watching these videos for your comments, useful comments. Please keep watching, and your input is very welcome. If there is any particular area of mathematics, specifically the IB or A-level math that you might want us to talk about, or that you might want me to do a video on, please let me know, and I will run through that for you. In this lesson, in this unit functions and equations, we are in lesson number 7, and in lesson 7 we'll be talking about implied domain. We started with relations and functions and looked at certain basic ideas, and now we are going into parts that are really critical in the study of functions, and the first of this is going to be the implied domain. We will talk about two types of implied domain. Of course, I'll be explaining what this means. The first will be the implied domain when it comes to square root functions, and the second one will be the implied domains for reciprocal functions, and then we'll look at a combination of both. Okay, so this lesson is going to be very short. We will only look at the implied domain when it comes to square root functions. But before that, what exactly do we mean? So one of the questions we want to answer today is, what do we mean when we say, when we use the word implied? What does it mean, an implied domain for a given function? Okay, we've already talked about domain and range, but then what does it mean, implied domain? And what is it if it is not implied domain? Okay, so in the study of this, we will look at specified domain. So effectively, if a domain is not implied, that means it is specified, it is given to us, all right? And we'll talk about some of the restrictions you see when a domain is specified for us, right? Secondly, number 3, we'll look at some relevant mathematical axioms, or what we refer to as mathematical ground rules, on which some of these some of these restrictions or implied domains will be derived from. Okay. The fourth thing we will look at, we will look, of course, at the implied domain of a square root function. Okay. How to determine the implied domain of a square root function, how to sketch the function given implied domain, and how to find the range after we have determined we've sketched the graph, all right? And after that, of course, we will look at some questions, and I will put up some for you to try out yourself, all right? So without wasting any extra time, let's move on. I've started with an opening problem so that you understand exactly what kind of questions we aim to be able to answer here. This opening question is coming directly from a past paper, IBSL paper 1 question, right? Here we go. A function f is given by f of x is the square root of x minus 2. Find the domain of the function. So in this case, a domain has not been given, and we are being asked to find it, okay? Express your answer in set builder notation. Okay, so let's start by understanding what we mean by a specified domain. So normally, when a function is given, it is also standard practice that we give the area of the function that we are interested in. So if we are given a quadratic equation, we want to know the area under which we want to consider the quadratic equation. For which values of x do we want to be looking at this particular quadratic equation, and so on. So it is important that we specify an area of, or a domain area where the function is going to be relevant, right? So it is common practice that when a function is given, such as these ones here, so I've taken this also from a past paper. Here, this examiner gives 3 different functions, and as you can see, in each case, a domain is specified. So it's for the first one there, which is an exponential function. it says this is an exponential function for which the domain is all values of x in the real set. Okay. The second one there also indicates that the domain is the real number set other than 0. So it means all possible values of R. X takes all possible values except 0. Right. Similarly, the secant of x, that is a trigonometric function. Again, the values of x are all acceptable from negative infinity to positive infinity. All right. So when a function is given, it is common practice that the domain for which the function is being specified is also given to us. All right. Here are other examples where a function is provided together with its domain. All right. So the first one you see there is a quadratic function. All right. And while we know that a quadratic function, the values of x can take any size from negative infinity to positive infinity, in this particular case, a domain has been specified for between -1 and 1. So we are only interested in this section irrespective of the fact that any value of the domain could be used. All right. Here are others. That's a sine function, which is a trigonometric function. Typically, we give the domain either in radians or in degrees. So pi radians is equivalent to 180 degrees. So in this case, from -180 degrees to 180 degrees. All right. There is a reciprocal function there. We will be talking about the reciprocal function more. Again, a domain has been specified. So if I wanted to ask you a question about any of these functions, here is a quadratic function there again. If I was going to ask any question about this, I would say, all right, investigate this function for values of x starting from this to that point, right? From one point to another. And that would be referred to as the specified domain, right? Last there is a logarithmic function. And again, in the case of the logarithmic function, we are being told that you are investigating this for values of x that are less than 1. Yes? Okay, so those are examples of a domain that have been specified for us. Okay? With the information about the domain, we can then go about sketching the graph and use that graph to determine the range of the function. Okay, so here is an example with the first one there. I think I sketched 2 of those 5 examples. So here is the first one. So while we know that the quadratic function can start from, so the quadratic function is a parabola. So this should effectively continue like that and pass through 2 and up there like that. So the quadratic function should look like that. But we are only interested in the specified section of, in the specified domain, and that's why we don't need to include this section of the graph, okay? And so once we have sketched the function like that, it becomes possible for us to determine what the range is. So for this specified domain, we can now talk about the range being the values of y from 0 to 6, all right? So given the domain, we can find the range of the function, as being between 0 and 6, okay? All right, the next one, that's actually the last function that I gave in the previous section. This is the log function, all right? And here the domain has been specified as coming from -9 to 1, okay? We can sketch it, and after we've sketched it, it becomes possible to determine the range. Now, when you look at this function, you can see that the graph comes and kind of tries to avoid line x equals 1. So it's just on that side of line x equals 1, which tells you that x equals 1, that vertical line there, is an asymptote to the curve. But either way, given this domain, we are able to find the range, where the range should be anywhere from -infinity to a value of 3 there, okay? And when we draw it, I think this is supposed to this should face the other way around because the infinity cannot be included there. So this should face out like that. Okay, so that is the range of that logarithmic function. Right, let's move on to the next part. Yeah, so we notice first of all that there is a, I think we've already talked about that, there is a vertical asymptote at x equals 1. So the graph does not pass that line onto this side, making it an asymptote. All right, let's move on. Now the next thing is I want to talk briefly about what we call mathematical axioms. Axioms are important in defining or giving us direction as to what we will do with the implied domain. Mathematical knowledge is based on some very basic understanding, some very basic as what we would refer to as starting rules, all right? Any piece of mathematical knowledge is based on reasoning, and this reasoning follows certain rules. And these basic rules are what we would refer to as mathematical axioms. So these are some building blocks of mathematical reasoning, and we define an axiom as a basic mathematical principle that is self-evident or explanatory and accepted as true without having to prove, right? So you will know that in mathematics, every piece of knowledge that we have, we want to try and prove its truthfulness. But even then, there are certain basic building blocks, starting points that we don't have to prove because they are self-evident. And these self-evident rules or axioms are what makes up what math is, what builds up math today. Okay, so why do we want to talk about this? Because there are aspects of what we are going to discuss, such as the implied domain, that will be based on this kind of reasoning. So here are some examples of mathematical axioms, really silly looking, really, but without these axioms, mathematics would be nowhere. So for example, some of the things we know but we just assume to be obvious are, okay, this is called the reflexive axiom, which is to say any number A has to be equal to itself. Of course, this is obvious. There is no way 2 could be equal to something else. But this has to be true for us to be able to do things like if a half of x is 8, and then we say, let's multiply both sides by 2, all right? So we can only do this because we believe that the 2 that we are multiplying on the left-hand side and the 2 that we are multiplying on the right-hand side have exactly the same property or are exactly the same thing. So a number has to be equal to itself in order for us to do stuff like this, okay? So looks rather obvious, but you know, we would not be able to do this if it wasn't true that a number is equal to itself, right? Sounds very silly, but then again, without these kind of assumptions or basic or ground rules, we would not be able to process mathematics as we might wish to, okay? A second basic axiom that I want you to I want to show you, yeah, that looks really, really obvious. But what about this? There's another one, the symmetric axiom, which says that if A equals B, then B must be equal to A. Okay? Yes, that's another mathematical axiom. Sounds really obvious, but we need to remind ourselves of these basic rules on which mathematical knowledge are based. Okay? A third one on algebra here is the transitive axiom. Okay? And the transitive axiom states that if a number A is equal to a number C, and a number B is also equal to a number C, then clearly A and B must also be equal to each other, right? Again, clearly that is obvious. Or maybe we just leave it. This is obvious. But let's look at, really boring, let's look at other axioms, say in geometry. So in geometry, one of the axioms, we'll talk about two of them. One of the very obvious axioms of geometry is that if there are 2 points in space, and you join them with a straight line, that straight line can be the only one joining the two. You can't have another different straight line joining those 2 points. In other words, there is only one straight line with the same gradient that will join those 2 points. So given 2 distinct points in space, there is exactly one straight line that contains them both. You can't have more than one, okay? The second one, and probably the last one, here's a diagram. If 2 lines L1 and L2 cross a third line L3, and if the angle they make with L3, angle A and angle B, are added together and the result is 180, we can conclude that line 1 and line 2 are parallel, right? Clearly, for some people that would be obvious, for the others it may not, but this is another example of a mathematical axiom on which a lot of geometrical reasoning is based, okay? So why are we talking about these axioms? It's because when we want to determine the implied domain of certain function, we need to go back to the ground rules about axioms. And some of the axioms we're going to talk about are coming up now. All right, so we can prove using those axioms, for example, that if we square a number, the result we get can never be negative. When we square a number, our result is always positive. So what this is saying is that for all real numbers, if we square a real number, any real number, the result will always be greater than 0, which means the result will always be positive. So the square of any number in the number line will always be positive. This is important because if all squares are positive, the reverse process must only involve positive numbers, right? Let me see if I can go through this. Let's use this flow chart. If I have a number that is positive or negative and I square that number, the answer I'm going to get is going to be positive. It's always positive, all right? So if we want to reverse the process of the forward process is squaring, the reverse process has to be square root. So if all squares are positive, then it is not possible to look for a square root of a negative number because there is no negative number in the first place whose square root you want to find, okay? This is the important key, all right? That we cannot find the square root of a negative number because there is no square that will give you a negative number to start with. This is an important result which comes from those axioms, all right? The axioms are used to prove this, and so by virtue of that, we can reason that negative numbers cannot have square roots in the real number line or in the real set, okay? So that is an important result that we've come up with there, that when we find the square root of a positive number, we'll get something. But we cannot find the square root of a negative number because there is no square that will give us a negative number here. If we could get a negative number here, then it's possible to process this to get back to a real number. But because the forward process can't give us a negative number here, we cannot find the square root of a negative number because it's not in this set of squares, all right, to be reversed, all right? Okay. So that leads us to the rule that we need for determining the domain, an implied domain of the square root function, okay? So I'm saying there that the fact that the forward process only gives us positive numbers means that the reverse process can only occur to those positive numbers and not negative numbers, which leads us to this rule here that a negative number has no square root in the real number set or in the real number line. You cannot find the square root of a negative number. Okay? Now, why is that useful? Now we go to this question. Find the implied domain and range of the following square root function. So let's start with very easy, all right? The number inside the square root sign is called the radical. It's called a radical. So the number inside the square root sign is called the radicand, or just in general, we call it the argument of the function, right? So the argument or the radicand in this case cannot be a negative number by the rule that we have determined. If you're going to find the square root of a number, that number would have to be positive by rule, by basic mathematical principles. So if this function really exists in the real number line, then the number whose square root, or the expression in there whose square root we are trying to find, has to be a positive number. All right, has to be greater than or equal to 0. Okay, if we are going to find the square root of 1 minus x, then 1 minus x, the whole 1 minus x, this thing here, this whole thing has to be a number that is positive or 0, has to be equal to or greater than 0. The same thing with the other functions, square root function that you're seeing in there. So, in short, if we're going to find the square root of a number, if these functions really exist in the real number set, then the radicands, okay, the arguments in there must be numbers that are either equal to or greater than 0. So let's see, let's find this for these 4 questions. So we start with this one. We reason, we look for the radicand, we go in and find the radicand. So here the radicand or the argument is x in there, and we reason using the rules that that cannot be less than 0. So we must say that x must be either greater than or equal to 0. So we say by rule 1 that x must be greater than or equal to 0. And right there is our domain, right? This is already telling us what our domain is. We can draw this on a line. All right, put the value of 0 as the boundary there. If we put 0 there, all right, this is telling me that this function is valid for values of x that are greater than 0 on the number line. So greater than 0 must be that way, okay? Like that. So this function can only occupy that side of the domain, or that side of the number line, and in that sense, this is telling me what the domain is. So this is an implied domain, okay? We can write the domain in a set builder notation. So already by just looking at this, this is a domain, but we want to write it in set builder notation. So we'll say x has to be real, and x has to lie between 0 and positive infinity, where 0 is accepted, but of course the positive infinity is not accepted. We can also draw the graph. Okay, the square root function looks like that. The square root function would be the inverse of the square function, which is the basic quadratic function, which is a parabola like that. We'll see how the two are related graphically. Okay? And what is the range? So when we have drawn the graph like that, it becomes possible to determine the range. In this case, the range is from 0 to positive infinity as well, with 0 accepted and positive infinity not accepted. All right, so we've done the first one. We've determined the domain of the square root of x. All right. Let's find the implied domain of the square root of 1 minus x. What is the implied domain for this function? We reason, once again, that the radicand or the argument, the expression under the square root sign, has to be greater than or equal to 0. Okay? So, if the radicand, which is 1 minus x, is greater than or equal to 0, then we can rearrange that so that we make x the subject, all right? So we have minus x equals, is greater than or equal to -1. And when we divide this by a negative number. You can say divide by 1 or multiply by 1. When we multiply or divide by 1, the sign of inequality flips. I hope you haven't forgotten that. And so this is now going to face the other side when we have divided, and we see that x must be less than or equal to 1. And this is our domain. We only need to write it in set builder notation. But before we do that, let's see how to present that on a number line. We want to present x is less than or equal to 1. So we draw the number line, put the point 1 in there, okay? And x is less than, so that means it has to be on this side, okay? Because it is less than 1. And therefore, when we draw the square root graph, we know that the graph is going to be on this side of x equals 1. Okay? So the domain then must be less than 1, less than or equal to 1, and greater than negative infinity. So in the same way, same way that we did the other one, this is then the domain of the square root of 1 minus x. Okay? This would be our implied domain. Okay? We can draw the graph, okay, because the graph is on this side. It looks exactly the same as before, position 1, and the graph has to be on that side. It has to be a square root graph, so it looks like that. So this is the general shape of a square root function. It can go that way or can go this way, but generally it will look like that. Okay? And the range is from 0 upwards like that, just like before. Okay, here's another one. We reason, you can pause the video and try it out yourself, but once again, we reason that the radicand, or the expression in there, 2x plus 5, has to be greater than or equal to 0. Okay, so that's the radicand there. It has to be greater than or equal to 0. When you rearrange that formula, 2x must be equal to must be greater than or equal to negative 5, and so divide both sides by 2. X must be greater than or equal to 2.5. You know, 5 of negative 5 over 2, which is negative 2.5. So that there is really our domain, but of course we want to write it in set builder notation. Before we do that, let's see which side that this graph is on. So we do a number line there and place x being negative 2.5, okay, negative 5 over 2 if you want, and x is greater than this. So that means the value of x has to be on that side. So the graph must occupy that side. You should already know, should already have an idea of how this graph is going to look like, because it is occupying that side of negative 2.5. And so if we sketch that function, first of all, the domain must be greater than. So starting from negative 2.5 or greater towards infinity. All right. And when we sketch the graph, we know the graph will be on that other side. Okay, like that. By the way, it is possible to find the coordinate of the y-intercept because at the y-intercept x is 0, so substitute 0 there, we get the square root of 5. So this point must be the positive square root of 5. Remember, square root of 5 can be positive or negative, so this must be the positive value of the square root of 5. Okay? Like that. So that there is the range. The range is from 0 upward. So once we know the domain and we've sketched the graph, it becomes possible to determine the range of the function. Okay? Here is another one. This is now a quadratic. The radicand or the argument of the square root function is a quadratic expression. All right? So we will say that that quadratic expression, the values of that quadratic radicand have to be greater than or equal to 0. And if we do that, yes, x squared minus 3x must be greater than or equal to 0. And if we rearrange that, in fact, in this case, what we want to do is to factorize. It's easy to factorize this one. If we do that, we get x into x minus 3. All right, so we have a product. We have a product of x and that bracket x minus 3. So if a product is positive, greater than 0 there implies that it is positive. So if the product of two numbers is positive, so if p times q is a positive number, there are two possibilities. One is that both of them are positive, and otherwise both of them are negative. Okay? If both of them are positive, then we are saying x is greater than or equal to 0 because it is positive, and x minus 3 and x, I'll write it here, x minus 3 is also greater than or equal to 0, meaning that x is greater than or equal to 3. So x must be greater than or equal to 3. So these are the options where the product is positive. So here the product of the two is positive. Okay? Alternatively, the two numbers being multiplied are both negative. If that's the case, if both are negative, then we are saying x is less than or equal to 0, and x minus 3 is also less than or equal to 0 because both are negative. When you multiply two negative numbers, you get positive. The product is positive, so two are either both positive or both negative. So this is already there, but this would mean that x is less than or equal to positive 3. So these are the cases that we have. Now we need to pick only one here that represents both and one here that would represent both. And let's reason. I can draw a line here. We want one case that represents both. So if I have 0 there and I have 3 here, the question is, if we say x is greater than 0 and x is greater than 3, which one takes care of both? All right, if I put a number here, let's take a number like 1. Well, 1 is greater than 0. Okay, it's greater than 0, but it is not greater than 3. All right, so it may be greater than a number that is lying between here is greater than 0, but it's not greater than 3. So we cannot pick this, we cannot take this one because there are numbers between them that will not satisfy this. But if I take a number here like 4, well, 4 is greater than both 3 and 0. So therefore, by taking x is greater than or equal to 3, I am representing this as well as that. So for this case, I will take those two. All right? This side is saying that the values of x is less than 0 and also less than 3. So which one is it that will represent both? Okay? We want a number to be less than 0 but also be less than 3. So if we come back up here, yeah, looking at the same, if I take a number here like 1, well, 1 is less than 3, right? It is less than 3, but it is not less than 0. Okay, so we cannot take this because if I take a number like this, it will not be less than 0. So if I take a number like -1, number that is less than 0, a number that is less than 0 is also less than 3. But a number that is less than 3 is not necessarily less than 0. 1 here, as we have seen, and 2 are less than 3, but they are not less than 0. So we want a number that is less than both 0 and 3, and therefore we go with this one here. So in this case, we go with this side. Okay, so what are we saying? We are saying that our domain must contain values of x such that x is less than or equal to 0 and x is greater than or equal to 3. So these are going to be my representatives of our domain. Let's see how that looks. Okay, so hopefully you've understood this. Let's see how that looks on graph. Inequalities that involves two values can sometimes be difficult to comprehend, but hopefully as we do more of it, it becomes more obvious. All right, so we will look at more questions of this nature, and hopefully it gets better as we progress. Okay, so we factorize. So we have the case, let me just go there now. So since the product is positive, since the product of this, so this product here, x and x minus 3, that product is greater than 0, meaning is positive. So since that product is positive, there are two possibilities. And the possibilities is that both x and x minus 3 are positive, or both x and x minus 3 are negative. All right? So either both x and x minus 3 are positive, or both are negative. So if x and x minus 3 are positive, then we are saying x is positive and x minus 3 is positive. Therefore, x is positive and so x is greater than 0 and x is greater than 3. So this one is coming from here by moving the negative 3 to the other side, all right? Okay, then the other option is that both are negative. We've already done this. So x is less than 0 and x minus 3 is less than or equal to 0. So x is less than or equal to 3, as we've done so. And based on the explanation I just showed, here we take x is greater than 3, and here we take x is less than 3, because x is greater than 3 represents both this. If a number is greater than 3, it is also greater than 0. All right? If a number is greater than 0, it is not necessarily greater than 3. So because of that, we pick this to represent the 2. Okay? Similarly here, x is less than 0, less than or equal to 0, or x is less than or equal to 3. If a number is less than or equal to 3, it is not necessarily less than 0. But a number that is less than 0 is also less than 3. So we take that one because it represents both, okay? So in this case, we'll take that one. And so this will inform our domain. In fact, that is our domain. So we draw this on a number line. Let's see how that looks. So one of them is at 0. The other one is at 3, okay? But it tells us that for the 0 one, x must be less. So this one, we must be taking values that are on this side. But here, x has to be greater than 3. So here, the values must be on that side. Okay, so 3 there. So values of x this way, right? X is less than 0, but on that side, x must be greater than 3. So our graph must be occupying those two spots, all right? Numbers less than 0 and numbers greater than 0, and nothing in between. Okay, so that must be our domain. Our domain must include all values of x that are less than or equal to 0, and those that are greater than or equal to 0, but not in between. All right? How does that look when we write it in set builder notation? This is how we would write it in set builder notation. Of course, you can also use the inequality signs, no big deal, but as we've said, this is a faster way of writing this. The union there means that we can take this or we can take that, right? Okay, and how does the graph look then? We want a graph that occupies 0 backwards and 3 onwards. So how does that graph look? We draw the y-axis, right, and the x-axis. We position 0 and 3. So that's 0 there, and we have 3. Okay, the graph for 0 and the graph for the 3 will go the other way around. And this is how the graph of this function looks like with the domain that we've mentioned. And what is the range of the function? As you can see, the range is from 0 all the way to infinity. Okay? Not difficult, really, when you think about it. Okay? So here is your turn. Here are 4 questions for you to try out. What are the implied domain and the range of these 4 functions? Okay? This is the end of this lesson. We will come to lesson number 8 after we have done this. So please try these questions yourself. Notice here that the square root sign reaches 1. It does not go beyond that. But if you think about transformation, you should easily be able to see this. Okay? So try it out and let's see what you get after this. Thank you very much. I hope you liked the video. If there's something that you did not understand and want us to go over again, just let me know and we will do that. In any case, we are also going to spend some time looking at your answers to this question, okay? In video, probably video number 9. Thank you very much and bye-bye. See you in the next video. you.